So now we know the basic elements in an electrical circuit, we're going to look at how circuits behave. The first thing we'll do is look at two basic rules of circuits, and those are Kirchhoff's laws. Number one is Kirchhoff's current law, sometimes called the junction rule. A junction is any point where several wires are connected together. The rule is that the total current going into a junction must equal the total current coming out of the junction. This follows from the conservation of charge. Since charge can't disappear, the total charge per second flowing in must equal the total charge per second flowing out. You can see in the example there, 7 amps going into the junction has split up into 5 amps plus 2 amps coming out. The second law is called Kirchhoff's voltage law, or the loop rule. Voltage supplies give a potential rise. We know that electrical potential is just the potential energy per unit of charge. Since equal amounts of charge are passing through all the components, we can see that the changes in potential are the same thing as changes in potential energy around the loop. So power supplies give a gain in potential energy, and resistors lose electrical potential energy because it's being converted to other forms. Kirchhoff's loop rule is just a statement of the conservation of energy. Its analogy for gravity is shown in the picture of the water feature. The voltage supply is like a pump that raises the water to the highest gravitational potential energy. Then each resistor around a loop is like a drop in height until you get to the lowest level. Notice it doesn't matter what the lowest level actually is. This water feature would work the same if it was at sea level or up on a mountain. In electricity, the only thing that matters is the difference between high and low potential, not what their absolute potential is relative to the ground. You can see in the circuit there, we have a potential difference of 12 volts, but we don't know what the absolute potential is at any point on that circuit. It doesn't show if it's connected to the ground or not. The only thing that matters are the differences. So you can see that the 12-volt potential rise we got from the power supply is equal to a 10-volt drop across the 5-ohm resistor plus a 2-volt drop across the 1-ohm resistor. Kirchhoff's two laws plus Ohm's law are all you need to analyze many complicated circuits. So let's look at the two types of circuit. Firstly, the series circuit. The resistors are all in a row so that the same current passes through each. We can use Kirchhoff's voltage law and Ohm's law to find an expression for the total resistance. This is sometimes called the equivalent resistance because any combination of resistors in a circuit could be replaced by a single equivalent one that gives the same current for the same voltage. So here we can see from Kirchhoff's law that V equals V1 plus V2 plus V3. Also, V equals IR from Ohm's law. So we get I times RS, which is the resistance of the series combination, equals I times R1 plus I times R2 plus I times R3. The I cancels out since it's the same everywhere. So we get the rule for a series circuit that the equivalent resistance is just the sum of all the resistances in the circuit. Now for resistors in parallel. Here you can see that the electrical potential all along the wires at the top is the same as the high potential from the supply, because we assume that the wires have no resistance and therefore there's no potential drop across them. Similarly, all the wires at the bottom are at the low potential, so that means each resistor in the parallel circuit has the same potential difference across it. Kirchhoff's current rule tells us that the currents in each branch must add up to the supply current. So now we have that V is the same for each resistor, and I equals I1 plus I2 plus I3. Using Ohm's law, we have that I equals V over R, so V over RP equals V over R1 plus V over R2 plus V over R3. Now the V's cancel out, and that leaves us with the equation for the equivalent resistance of resistors in parallel. So 1 over Rp is the sum of 1 over each resistance in the parallel circuit. Let's start by looking at quite a simple example. We want to know what current will flow through R1 when the switch is firstly open and secondly closed.